Hey everyone, my name is Barrett, and today we will be going over what is a stack. And now, a stack is a data structure that is very important within computer science. It's very similar to a queue, more further away from trees and BSTs, but it is still very important whenever it comes to memory management specifically. And there are two ideal ways to implement a stack. First, we have our array, and we have our linked list. Now, in an array, arrays are zero indexed, which means that the first box will always be index zero. So this is index zero. Um, let's fill this array up with some data. Let's say we have 1, 2, 3, 4, and we wanted to access the number 2. We would have to go array at index 1 because it is at the first index and everything starts at 0. So technically, this array has a size, or has this many elements. The size is equal to 4 because there are 4 elements in there. Now, this is an easy way to add things into an array because size will always point to the index after the last element. So size 4 means this box right here. So if I were to add something at size, it would put it at index 4. And length is something that is different. Length is how long or how much space the array has itself. And so this array has spots for 7 items. 7 items. Because it starts at index 0 and it goes all the way up to 6, so it'll be 6 plus 1. It has a size of, or a length of 7. And now let's go over linked lists. Linked lists are basically nodes that each have their own data within them, and then they have a pointer to the next node. But unlike how you can access things in the middle of an array, you cannot with a linked list. Linked list, you must start at the beginning. So in order to get to index 3, you would have to go from 1 to 2 to 3. But anyway, for this example, we will be using an array-backed stack. And let's get over what a stack is. We don't exactly need this. We already went over how length and size work. And so a stack is a first in, last out structure, or simply Philo. Now, there are other structures that are first in, first out, such as a queue. Queues work like this. If you're waiting in a line and you're the first one there, you're going to be the first one that gets into whatever you're waiting in line for. But a stack is the opposite. And so the best way to look at this is, let's say we have a stack of paper. In a stack of paper, you can only access whatever is on the top of the stack of paper, or the last page that you put on it. So let's say you had pages, like let's say you had a homework assignment that was all stapled together. Or not stapled together, just all on top of each other. So you had page 1, page 2, page 3, and page 4. Now immediately upon looking at the stack, or what we'll get to later as a peek function, you will only see the top page or the most recently added one, which will be page 4. And in order to get all the way down to page 1, you would have to take off page 4, take off page 3, and take off page 2 in order for only page 1 to be remaining. Now let's look at how to do this push, pop, and peek within functions. So let's say we have an array that has 5 elements, 0 through 4, and let's go over how some of these functions would work. And so push pushes data at size, like we said earlier. It will put it at the most, or the closest available spot in an array. So if we were to push 5, it would go to size. Size is currently 1, 2, 3, 4, 5. So it'll go to index 5, because this is index 0, 1, 2, 3, 4. So index 5 would be this. It would set this from null to 5, and the push function would be done. The pop function is how you take things off the stack. And so now it started at size 5, and now we're at size 6. And so pop will do array size minus 1. So since size always points at the index that is after the last element, or points as this null, In order to remove the last element, you need size minus 1. And so to go to size minus 1, which happens to be index 5, it will set this to null. Null. Size will go back down from 6 to 5, and then you're done. And now there are special cases where if you run out of space, the array can resize itself, but that is not exactly important in this example. The peek function is almost exactly what it sounds like. It will look at whatever is the last added element without actually changing the data at all. So it will look at whatever is at also size minus 1. So since we're still currently at size 5, it will go to index 5 minus 1, 4, and it will just return 4. And so, specifically within cybersecurity, this has very many important uses. And so first we're going to look at a function. And so in this C function, I will be using C for most of these examples, we have something called local variables. Local variables happen in many different functions for just various uses. Maybe it's setting numbers equal to each other, booleans, all sorts of things. But we're going to assume we are in a 32-bit system in which an integer has a data size in memory of 4 bytes. And so memory has a stack, memory stack, and that's where the local variables get put. And so memory specifically grows downwards into larger addresses because we start at address 0 and we move down to, I don't know, address FF. Since this is in hex, and we will go over hex in a later video. But since it is a FIFO structure, and A is the first thing to be set, we will be setting A to index 0, and then B at index 4, since they're each 4 bytes, and then C at index 8. Now this will have some very important things that happen in the future, specifically whenever we get to buffer overflows. And so make sure you watch this video before you watch buffer overflows. And thank you very much. That's all for today.